Deep learning has revolutionized artificial intelligence, powering everything from image recognition to language models. But training very deep networks hasn't always been easy. In fact, one of the biggest challenges researchers faced in the early days was the problem of vanishing and exploding gradients. In this video, we'll explore what these problems are, why they happen, and how modern techniques have largely overcome them. To understand the issue, let's start with gradients. When training a neural network, we use a process called backpropagation to adjust the weights. Gradients measure how much a change in each weight will affect the overall loss. If the gradient is large, the weight is updated significantly. If it's small, the update is tiny. The problem arises when these gradients don't behave well as they flow backwards through many layers. In the vanishing gradient problem, as we move backwards through layers, the gradients become smaller and smaller, often approaching zero. This usually happens when we use activation functions like the sigmoid or tanh. For example, in a sigmoid, values are squashed between 0 and 1. The slope of the sigmoid never exceeds 0.25. When gradients are multiplied across many layers, they shrink exponentially. By the time they reach the earlier layers, they're practically gone. The result? The early layers of the network stop learning. The network becomes stuck, unable to capture complex representations. The opposite can also happen. In the exploding gradient problem, gradients grow exponentially as they move backwards. This often happens when weights are initialized too large, or when the network is very deep without normalization. Here, instead of fading away, gradients blow up, leading to extremely large updates. The model becomes unstable. Weights oscillate wildly, and the network fails to converge. In practice, training either diverges or produces meaningless results. Both vanishing and exploding gradients slow down or completely halt learning. In the 1990s and early 2000s, this made it nearly impossible to train very deep networks, and progress in deep learning stalled. Neural networks with more than a few layers just wouldn't work in practice. Fortunately, researchers developed several powerful techniques to solve these problems. Let's go through the main ones. 1. Better activation functions. The introduction of ReLU, the rectified linear unit, was a breakthrough. Unlike sigmoid or tanh, ReLU doesn't squash gradients across most of its range, helping them survive through many layers. Variants like leaky ReLU and GeLU further improve stability. 2. Careful weight initialization. Instead of random initialization, methods like Xavier initialization and He initialization balance the variance of activations across layers. This prevents gradients from shrinking or exploding as they propagate. 3. Gradient clipping. When gradients become too large, we can cap them to a fixed threshold. This prevents exploding gradients from destabilizing the model. 4. Batch normalization. By normalizing activations layer by layer, batch norm keeps values within a stable range. This reduces the risk of both vanishing and exploding gradients, and it speeds up training. 5. Residual connections. Introduced in ResNets, residual connections allow gradients to flow more directly through very deep networks. This made it possible to train hundreds of layers without suffering from vanishing gradients. These solutions didn't just fix a technical annoyance, they opened the door to modern deep learning. Residual networks transformed computer vision. LSTMs and GRUs overcame vanishing gradients in recurrent networks, leading to breakthroughs in natural language processing. And today's large models, like GPT and vision transformers, simply wouldn't be trainable without these techniques. In summary, vanishing and exploding gradients were once considered major obstacles to training deep neural networks. But through clever ideas, new activation functions, smart initialization, normalization, gradient clipping, and architectural innovations, we've largely overcome them. Without these advances, the deep learning revolution might never have happened. Thanks for watching, and if you found this helpful, don't forget to like and subscribe for more deep learning insights.